Refining LDA in DFT by a dimensionless position and field sawtooth step function by element. Now, we're all used to this odd-even nature of the periodic table in different elements. Basically, as you go along, there's an odd, then an even, then an odd, then an even. It goes up and down, okay? And the presentation here is that this has 3D engineering underneath of it, classical physics to explain it. Basically, the first step is always 8/7, okay? That is, it is not isotropic, it is not ubiquitous, so you can't follow the original Gauss laws that say you're just stuffing them in evenly because it's different, okay? There are two hemispheres, and I'll explain this. Also then, for the second one, now you've got one hemisphere and the other hemisphere, and in combination it is. So for n divided by 2, you can use 4/3 pi r cubed as the volume, and you can use and apply Gauss and get the second step. But that's then bringing your average down, up, down, up, down, up. And this is how it works. It's the combination of 1/8/7 and 1/2 to the 1/3. And it becomes the sawtooth step function that we see in many thermodynamic, electronegativity, and other chemical calculations. Now, why is it sawtooth and step function? Let's talk about the nature of the periodic table. Typically in the textbook, it's called 2 times n squared. The first row is 2, then 8, 8, 18, 18, 32. But if you think about it, that's 2 times 1, and that's 8 is 2 times 4, which is 2 squared. The next one, 2 times 9, which is 3 squared, and 2 times 16, 32, but that really is 4 squared. However, I'm going to present this and say it's differently. It is one hemisphere, then the other. So instead of being, it's n over 2, and then you do the square. And that actually works better. As we know, Rydberg's n over 2 fails. It only works for hydrogen and hydrogen-like elements, okay? But when I restate it as this, it's going to work better. The second part is the nature of poly pairs. What I'm saying is that when you have a poly pair, the next electron wants to be as far away as possible. That is basically the 180 locked at pi radians position. That means relative to the nucleus, it is at 2 apart. And what you're missing is this extra 1 over r. So 1 over distance squared versus an r is 1 over distance cubed. So 1/2, twice as far away, 1 over 2 cubed is 1/8. And so once you do 1/8, you have an electron attracting you at 1, and that the electron to proton is attracting at 1, but that electron at the locked-in position, when you have a full set of pairs, 2 hemispheres, it's 2 away, so its strength is 1/8, but in the reverse direction. So that's 7/8, which means that your pair sits at 8/7 of the distance for 7/8 the strength, still gets you an equilibrium. 8/7 times 7/8 equals 1. Okay, that means that the implied math is this step function, the sum of the odd counts at 8/7 and the sum of the evens at this n divided by 2 of 3. Now, this scaling is not quite so easy, okay? It's not what Rydberg said, but it really has to be done understanding that 1 over distance squared really doesn't help you much. You have to have that. And the rule that I always apply and teach is that, except for, 4/3 pi r squared is a sphere, when you have exponents, especially these 4/3, 3/2, these fractional exponents, the inside must be dimensionless. That's why you get the dimensionless fine structure of constant, or as I call it, a factor, scaling factor. Okay, so as you hear down, instead of doing 1 over distance squared, so for example, LDA that we're talking about here is presented as r to the 4/3. And what I'm going to do is say, no, this is 1 over distance divided by some base. Okay, that base will determine to the 3/4. Okay, and that then has to be applied via these step functions and the mass functions, because obviously as you add a different isotope, you also have some additional small changes. So these are the steps that you use in our approach. Now, when you get out there, though, this also leads you to understanding that the outside shells may not be a full set. They may be longitudinal rings, but you might not have a noble gas. You might have, just the S shell, column 2, or just the S and the P shell, column 8, okay? And so thereby, we now have a path to get from the equation from the prior page to an actual averaging of those outer shells. Now, today we already do this. It's called hybridization. Okay, so when you do that, you basically have your step function, and then you have to average out what the extra ones out at the final positions is going to be. Now, all this follows from a hemispherical model of the atom. Basically, for every electron in one hemisphere, there's a matching electron locked at 180 degrees, or pi radians, locked at pi, that basically makes it those longitudinal rings not really as much clouds, but more like ring springs with a set logic where they're all locked in these longitudinal rings, matching one hemisphere and the other hemisphere, growing from 1 at the pole, that's subshell S, then 3, then 5, then 7, with the addition of an equatorial when you have odd counts, which is not in any side, so it doesn't have to have the offsetting matching pair, but you can get full subshells only when you have an equatorial. And so the odd counts have this extra matching one. This is a new way of looking at the atomic model, but it then matches what we're trying to do in LDA. So traditionally, we've had Purdue's ladder, which is great. It basically went from above the green line here. We have localization, LDA, which is using that R to the 4/3. Okay. Then you went to meta GGAs and all these other steps. But I'm saying that within that, you have to first need this dimensionless. This R needs to be dimensionless. So it has to be distance over some scaling of A sub O. That's the Bohr radius, okay? And further, that S sub N has to be done based upon this Sawtooth step function of odd even. Now, in fact, that actually makes the math very simple, because I'm saying that this is the regular math order of operations. This for acceleration allocation. So if you look at these with parentheses and divisions and multiplications, the first thing you have to do is you've got to have the Sawtooth step function, number 1, matching with a proper scaling, in this case, the R sub E. That's the size of an electron, okay? And that's scaled against the distance at a particular time, okay? And that's done then as the 3/4, which comes from standard LDA, number 3. Then you get 1 plus that, comparing one to the other, and that's sort of a gradient where it'll naturally sort of flow to where you want without being the dramatic. If you didn't have the 1 plus, it would be a pure inverse, which would then go to infinity and require, Einstein's relativity. But when we do it this way, we can take out that relativity step. And so number 4, which means that the originators, Combe and Sham and those guys, had it correct when they were adding meta GGA and such. And now, of course, number 5 is time, because basically these distances occur with some delay for the fields to propagate. So DFT is really this process of fixing the equations based upon this equation instead of your typical acceleration equals force over mass. That Newton's second law needs this adjustment, and we've been doing that in DFT naturally. We've also been doing this in what's called rest mass versus others. This idea of a mass 1 times mass 2 over the sum of the masses for the center of gravity is a similar concept, and partially what we're doing in the meta GGAs, if you think about it in that way. So we have many methods to do this besides just DFT. So what is the physics for this? Well, obviously, if we're trying to put energy, we're trying to stuff it into the tightest configuration as possible. Obviously, we like Gauss, that's 4/3 pi, something, distance over some base, cubed, okay? And which now we're going to get that force of 1 over distance cubed, okay, inside there. But guess what? We have electrostatics, which are squared, okay? And we also have these other things, okay? So what happens is when you put that 1 over distance squared in there, now you use the Born rule of squaring that to get your probability. You now have that square becomes 4 and the 3. Well, that's the 4 over 3 that becomes, or the 3 over 4, depending on which side you're looking at it, of the LDA. Okay, so in this one tiny part, I think that we need to change element scaling to add a sawtooth. We need to refinements to make the ratios of protons to neutrons. Okay, and and specifically we need to make those segments as dimensionless when they are not just a pure energy volume of the sphere. If it's any function of that, effectively you're using the inside of that and applying it differently. And then the goal here is to make DFT, by adding these 2 layers below, work for more elements more consistently. Now, when I did that, you say, wait, we already have R. How can you put something divided by and not screw up all the existing calculations, which we've, after years and years, done correctly? Specifically, we've done things, and but guess what? We already do normalization, which nets them to a 0. So I searched and tried to find what was going on. Basically, what happens is, as much as I'm adding this equation, this S sub n, this S sub n is also offset differently in a factor of mass. If I take the mass of elementary particles for mesons and I chart them when scaled to R sub e over A sub o to the 3/4, again, that is the fine structure constant alpha to the 3/2, or this is the scaling for an A sub o versus an R sub e, which is what we were doing in the beginning. Then what happens is we get a pretty good R squared of 0.9761. But the ones that are off this trend line are off exactly 25% plus, 25% minus, 12% plus, 12% minus. Well, that the 12%, that's the 8 segments. So with another step, I get this R squared correlation to mass to be 0.9990, impossibly perfect, if I use 1.10342 minus 1.12 as here for the trend line. And guess what that ratio of 1.1032 is? That is 8/7 times 1/2 to the cube root, the number I already found. So amazingly enough, all that we're doing in elementary particle standard model now applies as the fixed rate for that. So if I put this correction in for DFT, but I use the correct the elementary particle masses, I basically am going out by r to the 4/3 and then in by r sub e over a sub o to the 3/4. The net of that is I get back, and the projections that are done with the abstract method work also. This ratio has multiple methods that are all coming to show it. So first, try to make your equations dimensionless when they are fractional exponents or exponents that are not the pure, energy volume. The second is to get other elements, we need to really think about adjusting LDA for this Sawtooth step function by element, this SsubN. And that basically means moving the ladder down. But if so, then I have one segment that can do 4 steps of the ladder with one equation. That's the fourth root of all of the calculations that we're doing. And this is going to improve processing time and other things. If you need more references, please see my book, The Mass Equation.